Physics has a scaling problem. It's relatively straightforward to calculate the magnetic field of a single straight wire, but real-world applications rely on continuous macroscopic objects, like rings and coils, where the geometry curves and the field lines bend. To calculate the massive, predictable forces generated by these complex shapes, we have to dismantle them mathematically. We break the continuous object down into infinitesimally small, straight segments of current. This relies on the Biot-Savart law. It is the core mathematical tool that defines the exact magnetic field contribution of just one of those tiny wire segments at any given point in space. Our objective is to use that law to derive the exact mathematical model for the magnetic field along the central axis of a perfectly circular current loop. We will construct the 3D geometry, integrate the resulting field vectors, map the internal field, and apply this model to an active mechanical system. This transition, translating micro-level vector additions into macroscopic field equations, provides the mathematical framework required to model electromagnetic behavior in curved geometries. This diagram maps our problem, evaluating a circular loop carrying a steady current. The loop has a radius r. We want to find the magnetic field at point P, distance x along the central axis. The distance from the loop edge to P is r. We start by isolating a single infinitesimal current element, labeled IDL, at the very top of the loop. A position vector r connects this specific element directly to our observation point on the axis. When applying the Biot-Savart law to this isolated top segment, we evaluate the cross product. Because the loop sets in a plane perpendicular to the central axis, the angle between the tangent current element and the position vector r is always exactly 90 degrees. The cross product mandates that the resulting magnetic field vector, dB, points perpendicular to both the current element and vector r. This forces the dB vector to angle downward, leaning away from the central axis. We break this angled vector into two orthogonal components, an axial component running along the x-axis and a radial component pointing away from it. Now we incorporate the loop's symmetry by highlighting a second identical current element at the exact bottom of the ring. This bottom element generates its own dB vector. Following the same geometric rules, it points upward, angled away from the axis. We resolve this vector into its own axial and radial components. Because these two current elements sit exactly opposite each other on a symmetrical ring, their radial components point in strictly opposite directions with equal magnitude. They cancel each other out to zero. This cancellation occurs for every paired element around the entire circumference. The radial fields destroy each other, leaving only the axial components, the dB sine theta vectors, to stack additively along the central axis. Returning to the mathematical derivation, we calculate the total magnetic field B by integrating these surviving axial components over the entire loop, from 0 to 2 pi r. We substitute the sine term using the dimensions of our right triangle, capital R over lowercase r. We also substitute lowercase r squared with capital R squared plus x squared. Integrating around the loop multiplies our constant terms by the total circumference, yielding our final derived formula for the macroscopic magnetic field along the axis. Mathematical symmetry serves as a strict computational tool here. It takes a complex 3D vector integral and collapses it into a highly manageable algebraic equation. Looking at this 2D diagram, we see the physical structure. The current flows out of the page at the top and into it at the bottom, generating magnetic field loops. You can confirm the field's direction along the central axis using the right-hand grip rule. We can test the integrity of our newly derived formula by pushing it to a physical limit. We evaluate what happens to the math if we move our observation point from the outer axis directly into the exact center of the loop.
This equation box outlines the logic. At the geometric center of the loop, the distance x along the axis drops exactly to 0. Setting x to 0 eliminates it from the denominator. The r squared term is raised to the 3/2 power, becoming r cubed, which cancels with r squared in the numerator, reducing the expression to a compact formula for the center field. To scale this single loop model into a physical coil, you simply multiply this final result by n, representing the total number of wire turns. A robust mathematical model must remain valid when pushed to its physical boundaries, reliably collapsing into simpler, known truths. We apply this predictive capability to a specific algebraic challenge. The text asks, at what specific distance along the axis does the magnetic field degrade to exactly 1/8 of its maximum strength at the center? We set up the core math by equating our formulas. Both sides of the equation share the permeability constant μ0, the current I, and a factor of 2 in the denominator. We isolate the variables by striking out these common constants. Cross-multiplying rearranges the remaining terms. We isolate the complex denominator, the quantity r squared plus x squared to the 3/2 power on one side. To dismantle the fractional exponent, we first take the cube root of both sides, simplifying the right side to 2r. Next, we eliminate the remaining square root equivalent on the left by squaring both sides. We are left with r squared plus x squared equals 4r squared. Subtracting r squared from both sides isolates x squared, allowing us to take one final square root. The math states that at a distance of the square root of 3 times the radius, the field strength drops to 1/8 of its maximum. This predictive power allows physicists to pinpoint exact field thresholds in physical space algebraically without taking a single real-world measurement. We stretch this model further, bridging classical mechanics and electromagnetism. Consider a physical ring carrying a static electrical charge, spinning mechanically around its central axis. The diagram sets the parameters. The ring has a radius a width d, a uniform surface charge density represented by sigma, and it rotates with a frequency f. The physical setup requires a conceptual pivot. A continuous mechanical object coded in static charge that physically rotates is mathematically indistinguishable from a steady electrical current flowing through a stationary wire. We capture this rotation as an equivalent current. Current is total charge divided by time. Because frequency is the inverse of time, current equals total charge Q multiplied by rotation frequency F. To find total charge Q, we multiply the given surface charge density, sigma, by the total outer surface area of our thin ring, which is 2 pi times radius a times width d. We insert that expression for total charge directly back into our equivalent current equation. Now that we've defined a standard electrical current variable, I, we plug this expression directly into the center field formula derived earlier. The radius a and constant 2 in the denominator cancel out, isolating the exact magnetic induction field generated by the physical rotation. The mathematical equivalence between mechanical rotation and static current means the steady-state magnetic field of a rotating charged body can be modeled using the same loop equations that govern stationary circuits. We began with a single microscopic current vector and used the Biot-Savart law to track its isolated magnetic output. From there, we constructed a macroscopic field model. Structural symmetry reduced a complex vector problem into a scalar integral, as opposing radial forces canceled to zero and the axial components combined into a single predictable result. The utility of this derivation lies in its scalability. It provides a foundational blueprint that works equally well for analyzing a small copper coil on a workbench or calculating continuous rotational charge distributions across larger physical systems.